Okay. Hello, I'm Hyorim Kang. I'm a student at Yonsei University and the leader of the team Yonsei CIP Lab. Our Yonsei CIP Lab team consists of me, Jinu Kim, Kyungmin Kim, Taeyang Kim, and supervisor Professor Sanju Kim. First, we express deep gratitude towards the organizers who held this exciting workshop. In addition, it is a great honor to present our method here. Thank you for giving us an opportunity to deliver this presentation. Then, let's begin. So, these are the table of contents, and as you all know, Generic Event Boundary Detection, or GEBD, is a task that aims to detect class-agnostic event boundary. Note that the annotation direction itself is very subjective, one level deeper than the whole video semantics. Since the target boundaries are just a result of natural human perception without a concrete criterion, we thought that it would be the most challenging aspect when we deal with the task. So, to solve it, we focus on the difference between the adjacent task, temporal action localization, or TAL. Unlike TAL, we don't have to match start, end of the action instance, nor identify the class of detected one. Therefore, we formulated it as a snippet-wise binary classification. In this setting, a positive sample is 0.25 second long video snippet which contains an event boundary, and negative samples are the rest ones. In this slide, we introduce the basic settings that we used for the GEBD task. As we mentioned at the former slide, we treat a video clip as an ordered list of short video snippets. For this, we utilized Kinetics pre-trained snippet feature encoders, following the prevailing convention of the TAL and OAD, online action detection. To be specific, we used Kinetics pre-trained TSN model and slow fast model, and considered 6 consecutive frames as a unit video snippet, or in other words, input tensor to the former mentioned backbone models. Then, the two snippet-wise features, TSN features and slow fast features, are concatenated along the feature dimension, resulting in 6400 size vector per snippet. Detailed information about our backbone can be found in our technical report. By the way, with these encoders, we now have the tensor-shaped B, C, T. Instead of B, 3, H, W, tau. This 3 refers to the RGB3 channels, and this 6 refers to the consecutive 6 frames. And this B, C, T, this tensor, is a list of one-dimensional vectors, and we can apply standard 1D convolutional networks or recurrent neural networks, or to deal with the longer temporal dependency transform encoder architecture to process them. However, we found the simple application of these networks with standard binary cross-entropy loss is not enough for the good performance. So, in this slide, we demonstrate the intuition for our method. The temporal self-similarity matrix, or TSM, is a square matrix that contains pairwise self-similarity score. For example, element at 2, 3 represents the similarity score between the second snippet and third snippet. Following the definition, the matrix is symmetric, while the diagonal element would contain max value. If you see these TSM, you can observe that the diagonal values are all yellow, meaning that they are the max value. So, now imagine the situation that the TSM of a certain video is given. Can you detect event boundaries from that? Probably yes, because we can observe some informative cues from the given TSM. Okay, let's see this TSM. The boundaries should be like here and here and maybe here. So what information that I exploited? I used the fact that TSM would show local similarity except near the event boundaries. Note that the local similarity comes from the video's natural characteristic. Adjacent frame contains similar content, while the drastic similarity score change results from the change of the video semantics that occurs near the event boundary. These figures would help you to understand the concept. So, our first attempt was to devise end-to-end approach. Encoder, which can be composed of comp1D or transformer encoder or a combination of both, encodes the snippet-wise feature. From that encoded feature, pairwise similarity are computed, resulting in this TSM. This TSM can be multi-channeled when we use parallel architecture for the encoder. For example, comp1 encoded feature and transformer encoded feature can make their own TSM, and stacking them along channel axis would result in two-channel TSM. For competition, we adopted this multi-channel TSM concept because we thought that different encoder architectures can capture different aspects of this feature similarity. And there is a decoder, which interprets that multi-channel TSM. We utilized the modified ResNet 18 architecture for the decoder. Note that including calculating pairwise self-similarity score, all the operations are differentiable. Both encoder and decoder are trained only by final BCE laws, okay, and trained from scratch. This approach worked when we adopt an encoder architecture that enjoys short receptive field but collapses in the architecture that has longer receptive fields, like transformer encoder. We thought that it's because there is no loss term that forces TSM to be informative. Gradients only from the BCE laws, the final laws, is not enough for the encoder. So, as a solution, we instantiated the former mentioned characteristic as an auxiliary loss term. Okay, consider the TSM that we already have. Okay, maximizing or minimizing certain elements value of the matrix would be considered as contrastive learning. For instance, let's assume that we want to maximize 2,3 value in the TSM. It means that the similarity score between second snippet and third snippet is maximized, which can be interpreted as a positive pair in contrastive learning. Okay, with the same flow, decreasing certain element value in the TSM correspond to negative pair in the contrastive learning. Keeping this in mind, let us come back to our loss term. Okay, our goal is to make TSM to be more informative, or in other words, prettier. So, to make TSM to convey desirable cues, we designed the following mask. Okay, the blue plus denotes the element that should be maximized, and red minus denotes the element that should be minimized. Gray zeros refer neutral samples, which are ignored when we compute the auxiliary loss. So with this mask, the loss term is calculated like this. Note that the similarity score between the snippet containing event boundary, this sharp sign, and the other ones here, this cross, and are considered as neutral samples, like the scores between distance samples, like this samples. Okay. With this auxiliary loss term, our network's schematic diagram looks like this. This Simpson head and the stop gradient operation here in this path here is strongly inspired by the Simpson paper. And to boost the finer performance, we additionally exploited the direct prediction path. We thought that since this direct path, this direct path would provide prediction in different perspective, and combining the prediction would be beneficial for the final performance. And this table displays ablation study of our method. We can observe that the naive TSM approach, this TSM path without contrastive learning, this does not outperform our baseline, this direct path. But the one with the auxiliary contrastive learning loss significantly improve the performance. We think that there would be some more interesting ablation study, but due to lack of time, we could not conduct them. We are planning to do them in our future work. So, thank you for listening my presentation, and here's address of our code and our technical report. Okay, thank you.